In this video, we are going to learn about vector fields, which are an important component of our work in the vector calculus unit. So a vector field assigns to each point in 2 or 3 space an object that carries a magnitude and direction, also known as a vector. So essentially, our inputs are points in 2 or 3 space, and our outputs are going to be vectors, either 2-dimensional or 3-dimensional. More formally, if D is a subset of R2 or 2 space, a vector field on D is a function f that assigns to each point xy in D a 2-dimensional vector f of xy. So this is formally stating what we just mentioned earlier about the inputs and the outputs. Notationally, we have a bold capital F to indicate we're working with a vector field. Written out, you may want to write it as an F with a vector symbol above. And that's going to be P of xy as the I component and Q of xy as the j component. So we have 2 scalar functions, P and Q, in terms of x and y that will define the I and j components of each vector in the vector field. And written with vector brackets, that would just be P of xy, Q of xy. I tend to favor the vector bracket notation just as a simpler notation, but we need to be able to identify both of these in dealing with vector fields. If we extend up 1 dimension, E is a subset of R3 or 3 space. A vector field on E is a function f that assigns to each point xyz in E a 3-dimensional vector f of xyz. So same notation, capital, bold, F, but now we have 3 components, so it's going to be P of xyz as our I component, Q of xyz as the j component, and R of xyz as the k component. So now our scalar functions P, Q, and R are in terms of x, y, and z. They define the I, j, and k component of the vector field. And with vector brackets, we're just going to write P, Q, R to simplify things here. So that's the notation and the process of a vector field. So if we want to create a vector field or visualize it, we draw vectors at multiple points in the plane. Each vector starts at the point xy that is being input to the vector field f of xy. Now this is important because our previous work with vectors in Unit 1, we emphasized the fact that vectors were not fixed in space. So for instance, the vector 2, 1 could be drawn anywhere. Could be at the origin, could be at the point 5, 3 as the initial point, and then draw the vector 2, 1. Now for a vector field, we have to refine that a little bit. Each vector starts at the point that was input to get that vector. Right? So let's go through that process to make a little more sense of it. So if we wanted to make a table just to really emphasize the idea of the inputs and the outputs here. So our inputs are points. So let's say we input 0, 0. In this particular vector field of 2, 1, the output is 2, 1. If we input 1, 0, the output would be 2, 1. Input, let's say 1, 1, the output would be 2, 1. So in this constant vector field, the output will always be the vector 2, 1. So now if we want to sketch a few vectors, we don't have to go too crazy. Obviously there's a lot of points in space. I'm going to scale by every 2 boxes equaling to 1 just to give a little more space here. You can choose a different scale if that makes sense for your notes. I would stay away from 1 box equaling 1. It's just going to get a little crowded when we start to draw some of these vectors. So we start at 0, 0. That's our initial point. And then we draw the vector 2, 1. So this is what I was discussing earlier, where each vector is fixed with the initial point equal to the input of the vector field. So then if we go to 1, 0, then we draw the vector 2, 1 from that point. You can see how close these vectors are going to be. If we go to 1, 1, then we're going to draw the vector 2, 1 from that point. And we can fill a few more in. I think we're starting to get a sense of what this vector field looks like. But let's say we go to 0, 2. 0, 2. Then we, from that point, draw the vector 2, 1. And let's say we go to negative 3, 0. Again, the output is the vector 2, 1. So basically, at any point in space that we want to input, the output is going to be the vector 2, 1. You can see I'm just filling a few more in. Now, if we were to draw every vector possible, you notice there's going to be some overlap. And that's something that we're going to deal with when we're trying to draw vector fields by hand, but we do have a way to deal with it, especially when we use a graphing program to help us with these vector fields. But right now, we can see the constant vector field. The movement is moving diagonally up to that top right part of the graph. Next vector field we're going to sketch by hand is xi plus yj. So again, we can just go through the mechanics of inputs and outputs for at least a few points, and then we'll graph. So if we input the point 0, 0, the output would be the vector 0, 0. If we input the point 1, 0, the output would be the vector 1, 0. Input the point 1, 1, the vector would be 1, 1. And let's say we want to go negative, right? Negative 1, 1. Then our vector would be negative 1, 1. So let's use this as a starting point, and maybe we'll fill in a few more vectors just to get a sense of what's happening in the vector field. Same scale as the last example, just to make things easier here for us. Okay, so 0, 0, that would just be the point there. No vector, right? There's no direction there. 1, 0, so we start at that point, then we draw the vector 1, 0 from that point. We go to 1, 1, we draw the vector 1, 1 from that point. Go to negative 1, 1, draw the vector negative 1, 1 from that point. So let's go fill in a few more. So if we went 0, 1, so start here, the vector would go straight up. Negative 1, 0, then the vector from that point would be negative 1, 0. 0, negative 1 from that point would be the vector 0, negative 1. And we can kind of see how this vector field is going to take shape, right? So that's in there. If I want to draw a few more vectors just to really emphasize, so if we go 2, 0 from that point, then we go vector 2, 0. Right, so along the axes, we're drawing from that point a vector of magnitude 2 in the same direction. And then if I go, let's say, to this corner point, let's say 2, 2, then that vector is 2 on the x, so 1, 2, 1, 2, and then 2 on the y, so there would be the terminal point. And we would draw that vector out. And we can do the same thing, 2, 2, just to complete. Let's finish out this, or these few vectors. And patterns definitely help us here, but you can tell even when I know what the vector should look like, it takes a little bit of time, right? So sketching these by hand can be a bit tedious. Now this particular vector field where all the vectors are pointing away from the origin does have a name. It's called a radial vector field. And if they were all pointing towards the origin, it would be defined the same way as a radial vector field. Essentially, the name comes from the fact that we can draw circles in the plane, and all the vectors that would be touching that particular circle would have the same magnitude. So for instance, the 4 red vectors on the axes would all be touching the circle of radius 1, and they all have a magnitude of 1. And then if we draw a circle that's a little bit larger for the other 4 red vectors, those 4 vectors would be touching that circle, and they would all have the same magnitude. And we would continue to look at circles moving away from the origin, right? So that's called a radial vector field. Now if we sketch the vector field negative yx, just for one more example by hand, and these do take a bit of time, so input, so we'll start with the same set of points, so 0, 0, vector output is 0, 0. 1, 0, the vector output would be 0, 1. 1, 1, the vector output is negative 1, 1. So this is a little bit more interesting because it's not that the point turns directly into the vector. Let's say negative 1, 1, then that would be negative 1, negative 1 as our vector. So let's see how this starts to take shape here. So same thing, we have our x and our y. We'll go every 2 boxes for a scale. And we'll draw a few vectors here just to get a sense of what this vector field is going to look like. So we have 0, 0, and then at 1, 0, we draw the vector 0, 1 pointing up. At 1, 1, which is that point where we ended, then we have the vector negative 1, 1, so that ends there. And then if we go negative 1, 1, the other point we plugged in, so that's negative 1, negative 1. And let's fill a few more in. So if we went 0, 1, then that would be the vector negative 1, 0. Negative 1, 0 would give us the vector 0, negative 1. And then from there, it goes here. And again, once you kind of pick up on the pattern, you can start to quickly fill vectors in. And let's say you went to 2, 0, then that would start with the vector 0, 2 going up. And then if you're at the point 2, 2, then that's going to be negative 2, 2 there. So you have this rotational movement in this vector field. And I think that's enough. We can fill in more blue vectors to complete it, but I think we have a general sense of what this vector field looks like. And this has a name. It's called a rotational vector field. And here the key, if we were to draw those circles again, we would get vectors that are tangent to those circles that we draw, right? That create rotation inside of the vector field. In this case, the rotation is in the counterclockwise direction. So again, just to point out, if we try to plot the vector at the point 2, 1, notice our initial point would be in the middle of one of the vectors that we drew. So when we have all this overlapping, the vector field could get quite messy. So our solution is to create a scaled vector field. So often when we're given the graph of a vector field, it's going to be in scaled form. We don't really know what the scalar is, but it's some scalar that allows us to clearly see the movement in the vector field and how the magnitude of a vector compares to the others. So these are the same 2 vector fields that we just sketched by hand, but in scaled form. So we can still see that the vectors close to the origin have a smaller magnitude than the vectors that are further away. We still see the fact that it's a radial vector field. All the vectors are moving away from the origin. And then to the right, again, we see the comparison of the magnitude of the vector as we move away from the origin. And we see that rotational movement as well. Another thing that we might see is a unit vector field, where every vector in the vector field is a unit vector, right? So essentially all of these are going to be unit vectors. And we can check that pretty easily by finding the magnitude of this vector, even in terms of x and y, and it should simplify to give us 1. And it's a good exercise to work through. It works out pretty nicely, but every vector has a magnitude of 1. Now here might not look perfect because some of the vectors got cut off along the edges, but if you focus on the center part of the vector field, you can see that all of these vectors do have the same magnitude. Now in this case, it's not radial, not rotational, so it's just an example of a different vector field. Another thing to point out here in this particular vector field is the origin is not going to be defined in this vector field. So when we talked about the definition on the first slide of being defined on a set D, in this case the origin would not be part of that set where the vector field is defined. Because imagine trying to plug the origin into this particular vector field. So something to take note of, that a vector field does not need to be defined at every point in the plane or in 3 space. Right? This is a good example to show one that is not. An example of a 3-dimensional vector field. So we remove the axes just so we don't have that confusion with the axes and the vectors. But we can see right in the middle of that box is going to be the origin. We can see that all the vectors move away from the origin. And the way that this vector field is defined is as xi plus yj plus zk. So x as our I component, y as our j component, and z as our k component. And if we were to plot this by hand, we would go through that same process, although it would be a bit more challenging to do so in 3 space. If you're asked to sketch a vector field in 3 space, usually it's a much more simplified version of a vector field. Maybe 0, 0, 3, for instance. And you're just drawing that vector at a few points in 3 space to try to visualize it. Now, why we study vector fields is their applications. So vector fields can be used to model forces such as gravity, electricity, and magnetism. So these are what we categorize as our force fields. Or velocities such as wind speed or fluid flow. And these we categorize as our velocity fields. A lot of physics applications here, but they are all nice. They all work really nicely and give us a sense of why we would study a vector field and how that we're going to carry these through to calculus computations, right? Finding work, for instance, in a force field would be one of the computations that we are going to learn how to do. One vector field, just to kind of emphasize the gravitational field for a moment. Gravitational field. Right, Newton's law of gravity, it's often shown in a physics course, so that's going to be F, which is equal to negative G, capital M, lowercase m, over magnitude of r cubed times r, where r is the position vector, x, y, z. So essentially, if you have 2 objects, right, the 2-body problem, put one at the origin, and then the other would be defined by this position vector x, y, z. Capital M is the mass of one of the objects, lowercase m is the mass of the other, g is our gravitational constant. This creates the gravitational field, which is a vector field. So one of the more significant vector fields that you could study. So I just wanted to point that out in our notes. So now, building on the idea of vector fields, we're actually going to go back to an idea we covered previously, which is the gradient of a differentiable function, which outputs a vector for each point x, y. And if you remember, the gradient first came up when we were studying the directional derivative, and the gradient vector itself gave the direction in which the rate of change of the function was greatest at the given point. Right? So we were very much focused on the gradient vector at a single point, whether it was to calculate the directional derivative at that point in a certain direction, or if we wanted to know what the maximum or minimum rate of change of the function was at that particular point, we use the gradient vector. If we change our perspective a little bit, and instead of plugging in a single point, just take the gradient in terms of x's and y's, well, then that means that we would produce a gradient vector at every point in the plane or in 3 space. And in doing so, you would create a vector field. So we can think of it as a vector field called a gradient vector field or a conservative vector field. So the 2 names really depends on what lens you're looking at this through. The gradient vector field is a more mathematical approach. That is how we find the vector field. We take the gradient of some scalar function f of xy or f of xyz. And then conservative is if we're focused on more of the physics side. It's called a conservative vector field because there's a conservation of energy. So then we start to incorporate the ideas of potential and kinetic. We need to recognize both of these terms because we could be asked a question that uses either of them. More formally, a vector field F on a set D is called conservative if there exists a differentiable function f of xy on D such that the following fact is true. And that fact is that the vector field f of xy is equal to the gradient of some scalar function f of xy. So essentially what this means is the vector field is made up of components that are the partial with respect to x of some function and the partial with respect to y of some function. And we'll create our own conservative vector fields just to get a little bit better grasp on what this means. But more importantly, later on in this unit, we're going to need to be able to find this function given a conservative vector field. Now we do have a name for this function f of xy, and we call this function the potential function of the vector field f. And that's because this function gives us a relationship between the potential energy at the point and its position. Okay, so because we get a relationship between the potential energy and position, we call this function the potential function of the vector field. And then the vector field is going to give us the forces because it creates a vector at each point in space. Now, something to note for yourself is that not every vector field is conservative. It may feel like it at times throughout this unit because we will focus on conservative vector fields and the properties that they have and some of the simplifications in our computations that they give us. But generally speaking, not every vector field is a conservative vector field. It has to have this property that the function, or the vector field function rather, is equal to the gradient of some scalar function. So let's actually look at this to understand what it means a little bit more clearly. So find the conservative vector field with potential function f of xy being equal to x squared sine of xy. So here we are starting with the potential function and we're trying to create a conservative vector field. Okay, so we're trying to create a vector field f of xy, and we're going to do so by finding the gradient of the given potential function. So if you remember how to find the gradient vector, it's the partial with respect to x and then the partial with respect to y. So differentiating with respect to x requires the product rule here. So 2x sine of xy plus rule, you're going to get y, so x squared y cosine of xy. So that's our I component. And then take the partial of the potential function with respect to y now. And the chain rule will give us x from that inner part, so x cubed cosine of xy. So when we talk about a vector field being conservative, this is what one might look like, where the I component is, right, this component is the partial of a potential function with respect to x, and this component is the partial of some potential function with respect to y. So if we extend that, where our potential function now is a function of 3 variables, we're looking for a 3-dimensional vector field, f of x, y, z. So that's the gradient of the potential function to create that vector field. So partial with respect to x is y cubed. Partial with respect to y is 3xy squared minus 2yz squared. And then partial with respect to z is negative 2y squared z. Now, it's helpful to create a few conservative vector fields on your own just to understand the mechanics and how we find each component. But ultimately, we're going to want to work in the opposite direction. We're going to want to take a vector field, figure out if it's conservative, which will happen in another video, and then find the potential function of that conservative vector field. So let's take a look at this question. We're going to approach it informally, but we're going to find a potential function for the conservative vector field f of xy being equal to y plus 1, x plus 1. So first thing, I am telling you that this vector field is conservative so that we know there is a potential function. That's going to be a skill we develop. And if it is a conservative vector field, that means this was the partial of that potential function with respect to x, and this was the partial of that potential function with respect to y. So if we just try to logically think through this, we need to take y plus 1 and go back a step before it was differentiated with respect to x. So what could that have looked like? So we could say that would have been xy plus x. Okay, so this is a possible potential function. Now to check that it works or doesn't work, let's now take the partial of that potential function with respect to y and compare it to the j component of the vector field. So that's going to be x and then no other term. So notice how this doesn't equal x plus 1. So if we can make an adjustment to our potential function so that it is x plus 1, then we'd have reached our goal. So we can very easily do that by adding a y term. So if we take a second shot at this, so x, y, and x were good, but then a y term would help out here. And we can quickly check the partial of this potential function with respect to x is going to be y plus 1. Partial of this potential function with respect to y is x plus 1, and that matches the I and j component. If you want to go a step further, we can add a constant here, because that wouldn't affect either partial derivative, so you could say plus 100, and that could have been another potential function that would have created this conservative vector field. But really this is more just setting the stage for looking ahead at things that we're going to do more formally in some of the upcoming videos. But for now, practice with your vector fields, get used to the notation, both for 2-dimensional and 3-dimensional vector fields, and understand what it means for a vector field to be conservative and have a potential function. With that, I'll see you in the next video.